So I'm going to try and set a new world's record on world's shortest or NEC's shortest mini lecture, because this is really well covered in the textbook. So we're just looking at nitration and sulfonation as our new electrophiles for electrophilic aromatic substitution, EAS. And the EAS step is always the same, always, always, always. It's always the, here is my rotten, weak pi nucleophile reaching out to grab my electrophile, giving me the carbocation intermediate. And I might as well give you some foreshadowing right here. As usual, we should be thinking about where will the carbocation form, but we'll get back to that later. And then the subsequent step is the elimination step, where you remove the beta hydrogen. Boom, you're done. So all we're going to cover in this mini lecture is how we make the activated electrophile. And it's really straightforward. You can see that you have a super strong acid in sulfuric acid, and you have a multitude of, holy cow, all kinds of nucleophilic atoms in nitric acid, HNO3. So the question is, where is it going to be protonated? And you probably would never guess that it would be protonated on the hydroxyl group, the OH. You would probably think, well, crying out loud, the most electron-rich atom is obviously that one, so that's where it should be protonated. And you know what? It probably is protonated there. But every once in a while, it's going to be protonated right here. And when it's protonated right there, what do you have? You have a fantastic leaving group. Woohoo! That baby's going to get kicked out in a heartbeat, and what do you get? You get this guy. Now, if that's not an electrophile, I don't know what is. This is the nitronium electrophile. You know, my nomenclature for these weird cations is not the greatest. Bottom line is, what I care about is that you realize that this is an example of an electrophile where actually the atom bearing the positive charge is the one that's attacked. And, of course, the nucleophile is our aromatic ring, and the product is ultimately this guy, which is nitrobenzene. So by taking nitric acid, catalyzing its activation with a little bit of sulfuric acid, and reacting this with benzene or an aromatic, we put a nitro group on our aromatic ring. Okay, so nitration and sulfonation. Boy, the nice thing is they're so similar. So what did we just see? We just saw protonation here to give you a good leaving group. So now we're going to see protonation here to give you a good leaving group. That leaving group would be this guy. And who do you suppose is going to kick out that leaving group? Just like the nitronium ion, we lose water and we end up with a powerful electrophile that happens to be activated because there's still that proton sitting on there. So this guy goes right there. Reaction with benzene. That should look familiar. That is benzene sulfonic acid. This is toluene sulfonic acid. If that was a methyl group, it'd be methane sulfonic acid. Change any of these to the chloride, and you've got the mesylate and tosylate, etc., etc. So nitration and sulfonation, really, really similar. One, protonation to make a good leaving group. That is water. And two, minus water with neighboring group assistance by the lone pair. So that is it. You generate a fantastic electrophile. Now, one thing you should notice about sulfonation is that here's our electrophile. Notice the double arrow. Sulfonation is actually a reversible reaction, and that will come back to play a handy role in chapter 23. All right, so let's look at things in a big picture kind of way. We just saw SO3 as a good electrophile and the protonated version as an even better electrophile. Well, you know what? We've already seen that kind of electrophile in the formation of chromate esters in those chromium oxidations we've studied. Very similar. Looks to me like those are both electrophilic atoms that get attacked by nucleophiles. You betcha. And we just saw the formation of this electrophile, which actually looks a lot like this one and this one and this one, where every last one of these is electrophilic at that center carbon because we've got electron withdrawing groups pulling electron density away from that center carbon. Oh, so you know what? All the mechanisms are the same. You may remember this is the Edmond degradation reagent. This is ketene. This is what we saw in the example we went over in class. So, throw in a couple more. What do these all have in common? They all have that center atom being a powerful electrophile because of the oxygen double bond, or in this case, sulfur and nitrogen. And in U, it's something like this. That's the powerful electrophile. Nature happens to use phosphates. Bottom line is, it's a huge, huge pattern. And you use those patterns to figure out what's going on. So we'll wrap this one up by looking at an example. Okay, Lewis acid right here that activates my bromine electrophile to make it Br plus for all intents and purposes. That allows me to make bromobenzene. Bromobenzene, well, bromobenzene plus magnesium, no mechanism required here. It's kind of magic, but somehow or other the magnesium inserts in between the carbon-bromine bond to give you the Grignard reagent. There's that electrophile again. So we've got oxygen, carbon, oxygen. We know this guy is a nucleophile. So we're making a carbon-carbon bond. We're making a carboxylic acid. The carboxylate got protonated in the workup. With the carboxylic acid, oh, look at that. Another one of those darn electrophiles. Ha! Right there. Okay, so we know we got ourselves a nucleophile here. Up, down, out. That makes a sulfonyl ester, but I got Cl minus floating around, so that kicks that out. And bottom line is I make the acid chloride. Acid chloride then reacts with a nucleophile. Nomenclature. I think that this is an amine that has two isopropyl groups on it. Diisopropylamine. That should react in an up, down, out to give me my final product, nomenclature N-diisopropyl benzamide. Hoo-wee! Make sure you know how to name amides. Diisopropyl. So that's referring to this. The N is referring to the nitrogen, and the benzamide refers to the rest of the molecule. Alrighty, so that's it except for one more thing, and that is that I need to keep you working on your nomenclature, so especially your aromatic nomenclature. What would you call this molecule? That is obviously orthodox. Get it? Orthodox? Orthodox? Okie dokie. See you in class.